You are moving right now. Not in the way you normally think about movement. Not the movement of walking or driving or the rotation of the earth that carries you through a day. Those are the movements you can feel, the ones your body has reference points for. The movement I am talking about is happening without your knowledge, without your consent, and at a speed so incomprehensible that the English language does not have an adequate word for it. Our entire galaxy is being dragged through space at approximately 600 kilometers per second towards something we cannot see, in a direction we can barely observe, by a force whose true nature we do not fully understand. This is the story of how we found out. It begins not with a telescope pointed at the right place, but with a number that would not behave. In the 1970s, astrophysicists were doing something that sounds almost mundane by the standards of modern astronomy. They were measuring the velocities of galaxies. Specifically, they were comparing the velocities galaxies were predicted to have, based on the known expansion of the universe, with the velocities they actually had. The difference between those two numbers, the predicted velocity and the observed velocity, is called a peculiar velocity. Peculiar not in the everyday sense of strange, but in the technical astronomical sense of unexpected, departing from the model. Under the standard cosmological model of the time, peculiar velocities should be small. The universe was expanding uniformly in all directions, and while individual galaxies would have some small random motions caused by local gravitational interactions, those motions should average out across large scales. No consistent directional flow should be detectable across hundreds of millions of light years. The universe should look the same in every direction at sufficient scale. It did not. The peculiar velocities were not small. They were not random, and they were not averaging out. Instead, galaxies across a vast region of space were showing a consistent systematic motion in the same direction. Not drifting randomly, not averaging out, moving together as a coherent flow toward a specific point in the sky. The whole neighborhood of galaxies, including our own, was streaming toward something. The question was what? The astronomers who first identified this flow were members of a group that became known informally as the Seven Samurai, a team of 7 astrophysicists who in the mid-1980s conducted the most comprehensive survey of galaxy velocities that had ever been attempted. They measured the distances and velocities of hundreds of elliptical galaxies across a region spanning hundreds of millions of light years, cross-checking their measurements against multiple independent distance indicators, building a map of how galaxies were actually moving rather than how they were predicted to move. What the map showed was unambiguous. There was a massive flow. Hundreds of galaxies across a region far too large to be explained by any known local structure, all moving in the same direction, all pointing toward the same region of the sky. Alan Dressler, one of the 7 samurai, named the source of that flow in 1987. He called it the Great Attractor. The name itself communicates the problem immediately. Not the great object, not the great structure, the great attractor. Because at the moment of naming, the thing doing the attracting was completely invisible. Not faint, not difficult to observe, not requiring a larger telescope. Invisible, hidden behind an obstacle so fundamental and so frustrating that it has its own name in astronomy. The zone of avoidance. To understand the zone of avoidance, you need to understand the geometry of our position in the Milky Way. We sit inside a flat spiral disk of gas and dust and hundreds of billions of stars. When we look outward from Earth in most directions, our line of sight passes relatively quickly through the thin disk of the galaxy and into the clear intergalactic space beyond, where we can see distant galaxies billions of light years away with no significant obstruction. But when we look in the direction of the galactic plane, the flat equatorial region of the Milky Way itself, our line of sight passes through enormous quantities of gas and dust and stellar material. That material absorbs and scatters light across a wide range of wavelengths. Visible light is blocked almost completely. The stars and galaxies and cosmic structures that lie behind that wall of material are effectively hidden from observation at optical wavelengths. The zone of avoidance covers roughly 20% of the entire sky. It is not a problem that can be solved by building a bigger telescope. A bigger telescope collects more photons. It cannot collect photons that have been absorbed before they reach us. The material in the galactic plane is simply in the way, and it happens to be in the way in exactly the direction where the great attractor sits. This is the detective story at its most frustrating. The evidence of the crime is overwhelming. Hundreds of galaxies are moving toward a specific point. The gravitational influence of whatever is at that point is measurable across a region spanning hundreds of millions of light years. And yet the crime scene itself is hidden behind a wall that ordinary investigation cannot penetrate. Astronomers had to find another way in. The first breakthrough came from working around the edges of the zone of avoidance rather than through it. Galaxies above and below the galactic plane, where the dust is thin enough to observe through, were showing clear evidence of the flow. And by mapping those galaxies and extrapolating the trajectory of the flow, astronomers could triangulate the approximate location of whatever was causing it. The sightlines converged on a region in the direction of the constellations Centaurus and Norma, at a distance of somewhere between 150 and 250 million light-years. But the most powerful tool turned out to be one that the zone of avoidance cannot block. Radio waves and X-rays penetrate the galactic dust far more effectively than visible light. In the 1990s, astronomers began systematically surveying the hidden region behind the zone of avoidance, using radio telescopes and X-ray observatories, looking for the structures that optical telescopes could not see. What they found was significant. The Norma cluster, not a massive concentration of galaxies at the heart of the Great Attractor region, became visible for the first time. It was a dense cluster of large old galaxies, many of them colliding with each other and radiating enormous quantities of radio waves. Here was a real physical structure at the location the peculiar velocity surveys had been pointing at for a decade. But there was a problem. The Norma cluster, impressive as it was not massive enough to explain the full scale of the flow. The peculiar velocities of galaxies across hundreds of millions of light-years implied a gravitational source of extraordinary mass, far more mass than the Norma cluster contained. Either the measurements were wrong, or there was more to the story. There was more to the story. In 2005, an X-ray survey called the Clusters in the Zone of Avoidance Project delivered a result that complicated everything. The survey confirmed that the Great Attractor was real and that the Norma cluster was genuinely part of it. But it also found that the original estimates of the Great Attractor's mass had been dramatically overstated, by a factor of 10 in some cases. The apparent signal had been inflated by a statistical effect called Malmquist bias, which causes systematic overestimation of distances in flux-limited surveys. The actual mass of the Great Attractor was substantially smaller than the original calculations had suggested, which created a new problem immediately. If the Great Attractor was 10 times less massive than estimated, what was producing the full scale of the observed flow? The galaxies were still moving. The flow was still real. Something beyond the Great Attractor had to be contributing additional gravitational pull. The answer was already out there, 600 million light-years away. The Shapley supercluster, first catalogued by Harlow Shapley in the 1930s as an unusually dense concentration of galaxies, had been known for decades as a large cosmic structure. But its role in driving the peculiar velocity flow of our local universe had been underestimated. As more precise measurements became available, it became clear that the Shapley supercluster, far larger and far more massive than the Great Attractor region, was itself contributing significantly to the flow. The Milky Way and its neighbors were not simply falling toward the Great Attractor. They were falling toward a much larger gravitational landscape that included both the Great Attractor and the Shapley supercluster as major components. The detective story had produced a second suspect. The most significant conceptual breakthrough in understanding this entire system came in 2014 when a team led by Brent Tully at the University of Hawaii published a paper that reframed everything. Using a new technique for mapping galaxy flows based on precise measurements of peculiar velocities across a vast region of space, they defined for the first time the boundaries of what they called the Laniakea supercluster. Laniakea, a Hawaiian word meaning immeasurable heaven, is the structure within which all the previously identified pieces fit together. The Milky Way, the local group, the Virgo supercluster, the Great Attractor region with its Norma cluster, all of these are components of a single gravitationally defined supercluster spanning approximately 500 million light-years and containing the mass of 100 million billion suns. The Great Attractor is not an isolated mystery object. It is the gravitational center of Laniakea. The flow that the Seven Samurai detected in the 1980s was not galaxies falling toward a single unknown object. It was galaxies flowing toward the heart of the cosmic structure they are part of, like water flowing downhill toward the lowest point in a watershed. The Great Attractor is the drain. Understanding the structure clarifies something that sounds alarming, but is actually not. The fact that our galaxy is moving toward the Great Attractor at 600 kilometers per second does not mean we are on a collision course with destruction. The Great Attractor is not a black hole. It is not a singularity. It is a dense region of galaxy clusters and dark matter, the gravitational focal point of our supercluster. Falling toward it is not falling into a trap. It is simply the normal gravitational behavior of objects in a large-scale structure. And here is the twist that makes the entire story stranger than it initially appears. We will never get there. The universe is expanding. Not just expanding, but accelerating in its expansion, driven by dark energy, the mysterious, repulsive force that is pushing the fabric of space apart at an increasing rate. The galaxies that are furthest from us are receding faster than those nearby. And critically, the expansion of space does not care about the gravitational pull of the Great Attractor. As we fall toward it, space itself is stretching in every direction. The Great Attractor is also receding from us because of the expansion, at a rate that over cosmic timescales will eventually exceed our speed of approach. We are falling toward a destination that is simultaneously approaching us gravitationally and receding from us cosmologically. In a few billion years, the expansion of the universe will overcome the gravitational pull of Laniakea entirely. The supercluster will not remain gravitationally bound. The structures that make up the Great Attractor region will drift apart as dark energy pulls the universe outward, faster than gravity can hold it together. The flow that carries our galaxy toward the Great Attractor at 600 kilometers per second will eventually stall. The destination will become unreachable. And all the structures that currently define our cosmic neighborhood, the Norma cluster, the Shapley supercluster, Laniakea itself, will dissolve into the expanding darkness as dark energy wins its long, slow war against gravity. there is one more layer to this story that is worth dwelling on. The zone of avoidance, the obstacle that hid the Great Attractor from direct observation for decades, has not been fully conquered. Radio and X-ray observations have revealed the structures behind it, but significant portions of the hidden region remain poorly mapped. Future instruments are being designed specifically to address this. The Square Kilometre Array, a massive radio telescope currently under construction in South Africa and Australia, will be the most sensitive radio observatory ever built. Its ability to penetrate the dust and gas of the galactic plane will give astronomers their clearest view yet of what lies in the zone of avoidance. What they find there may resolve the remaining uncertainties about the mass and structure of the Great Attractor region, or it may reveal something else entirely. Something that extends the flow further, adds another suspect to the case file, points toward another structure beyond Laniakea that has been influencing our motion all along, without anyone yet having the instruments to see it. The peculiar velocity surveys that began in the 1970s revealed that the universe at large scales is not the smooth, uniform place the simplest models predicted. There are flows and attractors and repellers, vast cosmic currents that carry entire superclusters of galaxies through space over billions of years. The Great Attractor is one node in that system, the most significant one from our particular position in the universe, but not the only one. The full map of those currents is still being drawn. There is, in fact, a structure on the opposite side of the sky from the Great Attractor that astronomers identified in 2017 called the dipole repeller. Where the Great Attractor pulls, the dipole repeller pushes. It is a vast, underdense region of space. A cosmic void so empty relative to its surroundings that its lack of gravitational mass creates an effective repulsive force, pushing our galaxy away from it and toward the Great Attractor. Our motion through the universe is therefore not simply the result of being pulled toward something. It is the result of being simultaneously pulled from one direction and pushed from another, a cosmic pressure gradient operating across hundreds of millions of light years, with our galaxy caught between the two forces and moving through space as a consequence of both. The dipole repeller was invisible for the same reason the Great Attractor was difficult to study. Mapping underdense regions requires the same comprehensive galaxy surveys that mapping overdense regions requires, and those surveys take decades to build. Its identification in 2017 added a new dimension to the velocity flow that the Seven Samurai had first detected 40 years earlier. The current we are riding through the universe has both a source and a drain. We are passengers in a galaxy that is moving at 600 kilometers per second toward a destination we cannot directly see, pulled by forces we spent decades learning to detect, in a structure whose full extent we have only understood for 11 years. The detective story of the Great Attractor is not closed. The case file has a suspect, a location, a mechanism, and a motive. But the investigation is still running, and the destination is moving away from us faster than we can reach it. Good night.